attached to our fertigation manifold, you will see our set of root zone sensors. Here we have pH, EC, ORC, and dissolved oxygen. We removed these from the internal reservoir in order to limit the interference of the wires with the plants growing inside. In addition, the circulation of the water through the manifold helps to keep the contents of the reservoir mixed at all times. We felt this may also help to promote an increased dissolved oxygen level in the root zone as well. You will notice a small flow meter built into the circulation line. This is to help create a closed loop system that allows us to ensure that nutrients are being circulated and delivered as intended. Just beneath our sensing zone up here, we have our treatment zone, where various adjustment solutions are pumped into the circulating water using peristyle pumps. pH is held between 5.5 and 6.5 through the addition of acid and base solutions. Through the use of timing constructs and state flags within our code, we were able to walk up the EC within the growing chamber as our plants matured. We added an AB nutrient solution as well as a calcium magnesium supplement on the 7th, 10th, and 14th of the month. By the final feeding, our target was an EC of 1.4.
We have listened to your feedback, and on top of our manifold, we have added a Raspberry Pi touchscreen. This displays all of our readings to our Adafruit IO dashboard. This helps give the astronauts a sense of purpose in between missions and makes them feel more involved in the growing process of their food. While the system was capable of operating autonomously, we could switch it to manual mode using our touchscreen in order to involve the astronauts. Our Adafruit dashboard is also capable of changing and creating thresholds. It was our initial intention to use thermostats placed on the underside of the leaves to help determine leaf temperature. Given that we couldn't handle the plants for 28 days, we needed a better solution. We were able to find IR temperature sensors that could be laid on top of our reservoir. We're inspired by the use of no-touch infrared thermometers that we see being used in the world around us these days. They grab temperature readings from the underside of the leaves as the plants mature. Comparing the leaf temperature to that of the air temperature and relative humidity, we were able to calculate the vapor pressure deficit of the growing environment. Our target was to maintain a VPD between 0.2 and 1.4 throughout the growing cycle. On either side of our growing chamber are PWM DC fans that act as both an air intake and exhaust system. These are controlled by the same motor hat that controls our peristyle pumps. The intake fan operates full-time in order to promote transpiration for our plants, as well as prevent the growth of any unwanted fungus. The exhaust fan is used to evacuate air from the chamber in the event that relative humidity gets too high and takes us outside of our intended VPD zone. In the event the VPD becomes too great, our intake fan will also shut down until the system returns to its intended levels. To date, neither of these measures has been necessary so far. For phase 2, we decided to bring the nutrient reservoir inside the container to meet the constraints of the challenge. We allowed for 8 planting sites on top of this chamber. Each side consists of coconut coir that is contained within a permeable mesh bag resting inside of a net cup. In order to promote root mass and take advantage of a deep water culture technique of growing, the roots of the developing plants are able to go through the mesh to access the nutrients below. There is an array of 4 capacitive moisture sensors within the growing plots that each take an average of 20 readings every 10 minutes. After running physical testing in the lab to determine the true moisture content of the growing medium based on their analog outputs, we were able to create a threshold to build the watering schedule around. To do this, we needed to incorporate a pair of ADCs into our circuitry as the Raspberry Pi does not have the ability to make analog readings. If at any point the moisture falls below 20%, 40 milliliters of water is distributed to the planting sites. Both the watering and circulation pumps are controlled by the relays that are triggered by the Raspberry Pi's GPIO pins. Across the back panel of the growth chamber are a series of sensors that monitor air temperature, humidity, carbon dioxide level, and luminosity within the chamber. The luminosity sensor serves as a check to ensure that there is no failure in the grow lights during our intended photo period. In the center of our control panel is a breakout PCB for all of our power and I2C connections. We custom built our own hookup wires and routed them throughout the system using a 22 AWG wire and DuPont pins. We're very thankful to the Growing Beyond Earth Challenge Phase 2, as this has given us an opportunity to present our work
As young engineers, it's been great to have this challenge, as working on the automation of food growth has been our main course of study throughout middle school.
Noah and I have really worked hard in this project, and even through the difficulties and challenges, we really just enjoyed ourselves and had fun with it. We are looking forward to continue to work and expand our project, and hope NASA and Fairchild can be with us on our journey.